Okay, let's go and get started. We'll continue our study of graphs, which could technically be the last data structure of this class, in case no one knew that.
What?
Whoa! Unless you want to do another one. Do you want to do
No.
another one? Like quad trees or odd
No.
trees?
Nope.
Really?
I would have rather stopped at like arrays.
No. So if you could just this would be the last lab and have the rest of the time here, everybody catch up, that would be great.
But like linked lists.
How about you have linked lists, double linked lists?
We already did
Man,
that
you
one.
just,
Just
it's
solid.
no fun. No fun.
I don't like that. It's fine.
No, it's doubly linked list is something else. But you can have a doubly linked list of doubly linked lists,
How
right?
about no?
What?
Um,
What's wrong? Name one problem with them.
It's
Too
hard.
complicated. Yeah.
It's not hard. You just have to understand, think about it abstractly.
I can't do that.
we already have a project where we had an array of arrays of arrays.
Yeah, let's not do that again.
That will-
All right. Well, let's think about a graph.
Okay, let's think about graphs.
So, someone explain to me what a graph is. I have two pictures here. What do you see?
It's a tree that
What?
can connect to other spots in the tree instead of just in a normal like. This one has like branches that can fuse.
Instead of a
Connect
tree,
anything
it
you
looks like a
want.
bowl of noodles.
Yeah.
Yeah, it's like a bowl of noodles. That works.
It's a bowl of noodles. What was another definition?
I was gonna say a graph is a grid, most often in the Cartesian format, although I don't know any other format, where it's an x and a y axis.
That's a 2D graph. That's lame. Let's go something else. How about a
You can
computer
also have
science?
a y axis as well.
Yeah, because many axes is.
Yeah. Why limit the number of dimensions? That's just silly.
Just, make
Jonah?
it most useful.
Sorry, I was reading the new expected gadget thing.
Oh, okay. Well,
He's not wearing his coat.
I'm not wearing my coat, so I guess this is no longer true. Anyone else
Okay,
want?
on the other board, that's the lizard.
So what does a graph contain?
Isn't this the
Information.
data structure that has that could have an unlimited amount of children?
Sure. All right. But I mean, do we have any type of parent-child relationship in a graph? Craig?
Not really. No,
No.
because the child can then connect back to the parent. And
Right. So the parent could be the child's child, which doesn't make any sense. Yeah. So there's no parent-child relationship here. So what do we have? We have
Bunch of things pointing to one another.
what's that?
Bunch of things pointing to one another.
We have a bunch of things pointing to one another. And what are those pointing? What's the pointing called?
An edge.
Okay. And what are the things called?
Nodes.
All right, there we go. So a graph is just a collection of nodes or vertices and edges. All right.
Okay.
So what does it mean for them to be adjacent?
means
There
they're
is one
connected.
edge and there tends to be on.
Okay. What does that mean? How does that make you feel? Does that mean they're connected some way
With an edge.
with a single edge or multiple edges?
One.
One. Adjacent means they're connected via one edge. And what's an incident?
Multiple edges? Oh, is
If
that on
edge E equals UV, then E is an incident. Right. An incident is the edge, one of the edges between 2 points. 2 nodes, sorry.
Oh, so the instance the edge.
Yeah, the specific edge. Because you can have more than one edge. Because you could have parallel edges. Why is so many things gross?
I don't know if it's gross as much as just.
So what's a path?
The way you get through the nodes,
All right.
the edges you follow.
The edges you follow. So what property must exist with all those edges?
It must have some sort of
Flow, you're on the right track, but they need to be
Connected.
connected. Sure, okay, we'll go with connected. Yeah, connected is a good one. Now what would be a cycle?
When it goes.
simple path in which the first and last are.
And what does that mean?
Go in a circle.
They go in a circle. All right, good job. All right, to write programs that process and manipulate graphs, we have to store the graph in memory. How are we going to represent a graph in memory?
That's a hot mess.
What?
That's a hot mess.
A hot mess? Hmm.
Well, we have arrays, we have queues, we have all those fun things.
And what would we use?
Whatever
What
options.
code we just need to start with one node, for instance. Let's just think like that. And at that point, other nodes.
Well, we normally use either arrays or
That's gonna have to be a vector area itself.
arrays or linked list.
Is it a matrix? Because it says matrices.
Yeah, so we can have.
Oh, right, so we could use what type of matrix? All right, matrices and lists. All right, so there's two main ways to do it.
Yeah, I was trying to come up with more fun answers.
I know, but I was having fun with it too. So you can use an adjacency matrix or an adjacency list. What is so common about those two?
Is there STLs for it?
No.
Dang.
What's the commonality between those two?
Adjacency?
Yeah, there we go. And what does that mean?
They're connected with edges.
There.
Right. So what this is real? What's that?
He said they're adjacent.
They're adjacent. Whoa. So really, these data structures are going to store the connection between nodes, the direct connection between nodes, aka they're storing the edges. Is really what we care about. Ooh, so a graph with n vertices and where n is greater than 0. Does it make any sense to have the amount of vertices be less than 0? No. No. But then we could use imaginary graphs. Wouldn't that be like imaginary numbers?
No, we're using those right now in linear.
What's wrong with imaginary numbers?
Everything.
Everything?
It's not real.
Right, they're complex.
Yeah, but why are we going to talk about them if they're not even real?
Because they're very useful to represent reality.
How could something irrational be used to represent reality?
Yeah, so.
Well, irrational is something different. Just because it's not the ratio of two numbers doesn't mean it doesn't exist.
Just because.
I know. So.
But it's not even irrational, I guess, rather it's unreal.
Well, it's imaginary, right?
Yeah.
Yeah, I love that, Dave. And then we started
Imaginary
using
numbers aren't really imaginary. They just can't be represented in our number system because of its imperfection.
Yeah, we have a little letter I. We can represent it. We can
It
represent
cannot
it.
be represented in the form of a number, though. That's a variable, a letter. You can't count to the imaginary number, quote unquote, imaginary.
Well, we could do half I plus half I equals a whole I. Oh well. Anyways, back to what we're doing here. That was a great sidetrack for no good reason. An adjacency matrix is a two-dimensional n by n matrix such that, for every element, 0 if there exists an edge and 1 if there does exist an edge. Adjacency matrix of an undirected graph is symmetric. I think this is going to be the entire slide on an adjacency matrix. Yep. All right, good. Wow, this is terrible. This is all we get? Okay.
Haven't we discussed this before? These slides are not the best.
All right, how do we want to do this?
Not painfully.
Yeah, not painfully.
Adjacency matrix. I probably misspelled that. Let's see, we'll include IOStream, int main, int argc, char star argv, and just realized y'all can't see this because it's on the command line.
What have we learned by now?
Learned what?
That working on the command line is not a good idea.
Oh no, working on the command line is the way to go.
Not when you're trying to type it for us.
Why? What would you have me use instead?
That. Why'd you put it full screen?
Okay. Would you prefer, you know,
In the front?
like that?
No,
Yeah, there it is.
Oh, you want it like this?
Yeah.
Okay. Oh, I see what you're saying now. Sorry. I'm sorry. I was just
We've
confused.
gone this whole semester doing it one way, and you want to change it to be a different way now? That's not how this works.
You need to have your mind, adjust to change. It's inevitable.
Have your mind open to possibilities, of course.
Right. You need to open your mind. Free your mind. There we go.
I watched that the other day. The more you know. It was on television.
It was?
Yeah.
Wait, hold
It was like they did like a marathon. I watched the first and the second one, but I didn't watch the third.
What are you talking about? There's only one movie.
The Matrix?
Yeah.
There's 3 of them.
No.
Well, the first one is the only like.
Unless you're talking like Star Wars, like the 4th one's the original Star Wars.
All right, we'll go ahead and include a vector.
There very well could be.
All right, so if we want to have a 2x2 matrix and we want to use vectors, how would we do that?
Declare a vector within a vector.
Oh, right. So we have a standard vector.
Can I open up a window? It's pretty hot.
Sure.
Turn up the humidity of your phone.
We'll have a vector of integers. We'll call it the graph adjacency matrix. Okay. And how many nodes should we put on this guy?
At least one.
At least one? You know, I always forget how to use a vector, so let's go look it up. C++ vector. I'm just used to using arrays instead, but y'all seem to like vectors, so we'll go ahead and do that. Change the size. That sounded great.
Hold on, there's a resize function.
I wonder if it works. am.resize. What do we want it to be?
12.
12? All right, so we'll have 12 nodes.
Sure.
And then the problem then is inside of here we got to do it again.
Or I could declare a global variable and we can change it all the time later.
That's what I just did. Let's see if this actually compiles. What do you think the chances are?
Yeah.
50%.
Oh, it did. All right. Maybe we're doing this right. Okay. So if we have a vector of vectors, so we have a 2D array, it's 12 by 12.
You're making the face.
What should the initial values be if there are no edges? 0. Okay.
36.
I'm making the face. So m graph. Well, actually, we got to do another for loop. For int j equals 0, j is less than 12, j plus plus. M graph am sub I sub j equals 0. And let's see if that compiles. Hey, it worked. But is that correct? Why is that not correct?
Why would you say about this graph?
Why would we say this JC matrix is representing our nodes? Ooh, let's go draw on the board.
Any pictures?
Who wrote that?
I don't know.
No idea.
Not a clue whatsoever.
Uh-huh.
All right, so 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Okay. So initially we have these all out to be zeros. Is that correct? Is there an edge between 0 and 0?
No.
There's anything.
Because it's a two-dimensional rectangle.
Well, I mean, if you're on the edge 0 and you want to go to 0, can you?
No.
Yeah.
Yes.
Zero.
Because you're at 0, you want to go to 0. Can you go to 0? Yes. Because we're there. So this diagonal should be a bunch of 1s, and the rest are 0s.
So wait a second. Because we're at 0, the entire diagonal roll should be 1.
Well, if you're at 1, can you go to 1?
Yes.
If you're at 2, can you go to 2?
Yes.
If you're at 3, can you go to 3?
C.
Now in French. Okay, 4, can you go to 4?
Just swap.
Yeah. Okay, but like, why did that have to make? Why did you have to make it 1 though?
So in this representation of a graph, which is actually a terrible representation, but we're going to stick to it because that's what the slide says, and then we'll actually do it the real way afterwards, is that a 1 represents that you can actually go from one node to another, and a 0 means you can't.
Okay.
Okay.
That's a photo.
All right.
So 1 basically just means this is travelable.
Travis.
Yes. So I'm going to make a little print function so we can see what it looks like. And what do we got here? 4. What's it? Vector of. Oh man, this is going to be a terrible iterator. Vector. Let's see. Of int. And do we have all that? Right. And we want the iterator it equals mgraph am dot begin. All right, this is just dumb. You can do it while it does not equal mgraph am dot end. It plus plus. What are the chances of this working right off the bat? Alrighty then. So you know you didn't ask me. Let me comment. So let's initialize the graph.
We're not really lively today, are we?
What's that?
We're not really lively today, are we?
Yeah, what happened, guys? It's because of the rain.
All I know is when I woke up this morning, I was debating life.
Whenever you ever like, I was 8 o'clock in the morning.
I was debating life.
I woke up and I was like, I gotta go to class, but I was trying to reason with myself on if I could cut chapel.
You know, I did a
That's
simulator.
why I'm here.
All right.
It was a difficult morning.
He thought that.
The morning.
He thought.
What dot begin, and then it does not equal.
ITT Technical Institute.
You do. Wow, this is actually really confusing.
Yeah.
That's why C++ is.
Interesting.
Yes, that was the right word. Alright, chances of that working are low. Oh, it worked.
Nice.
Huh.
Good job.
Didn't expect that to happen. Alright, I'm glad. But that graph is not correct, is it?
No.
Why? So what we need to do,
Just put ones
we need to put our ones in there.
In the diagonal.
So if,
I is equal to J.
right, equals, let's say, I equal to j, if that's so, then we want it to be 1, otherwise 0. Boom! There we go, much better. All right. So, we have this graph. We probably should add something, right?
Numbers.
Values.
Edges?
That's just my
Edges.
Yes.
I mean, right now we have 12 which are edges.
Yeah.
Okay.
Glad we got that
Wait a
out of the
second.
way.
They can edge refer to like.
An edge is basically a pointer.
Do we want to add directed edges or undirected edges?
Direct-
We'll add directed edge in start and end. All right. So let's say we're down here and we want to add directed edge from, where do we want to go? From 0 to 1. Wow, we're so original. All right, how would we do that? mgraph am sub start sub end equals 1. Right?
Sure.
Let's see if that did it. Hey, look. So you go from 0 to 1, we have an edge. So how would you add an undirected edge?
Random. Math rand. That's what I do.
What does an undirected edge mean? Why am I typing this out for you? A directed edge means you have a start and end, but an undirected edge means you go both ways. So what would you need to do? Add,
Start and then end, and then end and start.
there we go. So we can just copy paste our code, add the directed edge from start to end, and then from end to start. Right?
Yep.
Okay, I'm glad y'all are with me. So let's do an undirected edge from 2 to 4. Ooh, failure.
Would be great.
I forgot to decapitalize. I forgot to do something with the word end. Add directed edge was not declared in the scope. We'll fix your wagon.
What?
There.
Ah.
Ah!
Ah.
Ah!
Is that-
So
that doesn't
2.
look right.
What's that?
My light.
That doesn't look right.
Doesn't look right. All right, let's make our printing function better. We'll go. Let's see. How do we want to do this? Int. Let's see. Row equals 0. Column equals 0. So let's print the header first. Do I want to print the header first? Sure, let's print the header. Is it dot size? Y'all don't know? What is it? Vector dot size? How do you get the size of a vector? Come on, guys.
You ask it nicely.
Yeah, it is.
You ask it nicely. Whew! That was good. I liked it. All right, so we'll see. You ask it nicely.
I'm gonna be cracking up about that all day now.
All right, and then down here, after we ask it nicely, we probably should put in a space. All right, let's see if that pretties it up any. Oh, that was cute. Interesting.
Still not right, though.
I did the.
There you go.
It's still not right.
No, wait, no.
Y'all are so.
Picky?
Kind of.
Okay, that's better.
Still not right.
Oh my goodness.
The lemon is just kind of like there.
Just chilling.
Yeah. Just like, well, I couldn't fit on the graph.
I couldn't feel the graph, didn't know what was going on, so I decided to figure it
And they're all like 11.
out. 11. So we don't. Alright, let's get rid of this column variable. It's silly. No one likes it. And we'll do this one twice. Whoops. And now we'll put in some dashes, because that solves all problems.
Oh, I wasn't worried about the top. If you look in the actual thing, it's like all wonky.
Alright, fine. We'll fix the wonkiness.
No, like if you actually like looking at like the ones and the zeros aren't like aligned. Like diagonal.
Who writes this? All right, so.
Okay. Because if you look like at line 1, there's the 2 ones. Line, or well, line 0. Line 2 has 2 ones, and line 4 has 2 ones.
Can you add a space to the
Why does it have
0
4
through
ones?
9?
All right. Yeah, who does this code is going to be terrible.
Sorry.
Horrible.
IOMNet would be nice, but I haven't used that in forever.
Yeah, and last time I used it, only sadness occurred. But if this was regular C, this problem easy to solve. But instead we have to use C out, because that's what we use.
You should just put namespace.
Oh no. If we're going to use C++, we need to embrace its hideousness.
There, see.
I mean, we already discussed we don't want to put STDs in our code.
We're putting STDs in our code.
Can syphilis be one of them?
Jeff.
I use that making jokes.
Yes. All right. We'll get it done one day. All right. So the problem here is that if then you want to add you don't want to add it. You want to add it before, not after. There. Right. So now something is almost lined up, except we don't want to do it if it's 10. Phi is less than.
You have, never mind.
Hmm?
Never mind.
We'll get this lined up eventually. But today's not looking good. Alright, so now we need to go down here. And we need to add 2 spaces.
That's better.
That is a lot better.
Why is there still doubles of 1s though? Like in certain rows, like it's more.
Yeah, we're getting there. Hold on.
That's a bunch.
Oh!
That.
I think we might be done.
That's nice.
Alright.
Sure.
Does that help any?
Sure.
Yeah.
Just roll with punches.
Any other questions, comments?
I'm just worried about why there are multiple ones in each, in like some of the rows.
Why would there be multiple ones?
It's a good question. Why are there multiple ones?
Why are there multiple ones?
That's the
What does a 1
one
represent?
That you can make it. Oh, are those the 2 and the 4 that we put in the second?
Yeah, so you have you can go from 2 to 4, and you can go from 4 to 2. So the left hand is the start, and the row is the start, and the column is the end.
Okay. Well, what about the spot where it says 0, 1?
It says 0, 1 in lots of places. Which one are you referring to?
Row 0, column 1.
Mm-hmm.
There's a 1 right there. Why?
Because you can go from 0 to 1. But you can't go from 1 to 0 because we put in a directed edge.
Okay. Alright, that makes sense. What if this whole graph was 1?
If the whole graph was 1, what would that mean? You have a
They were all
connection,
connected.
which means the graph is
Circular.
fully circular and fully connected.
It's
It's
a hot mess.
a hot mess. All right. Bless you. Okay, where were we? What was I doing? Okay, let's add some more edges. What else do you want to add edges to?
6 and 12.
6 and 12? Undirected or directed?
Undirected.
Why can't we go to 12?
You're gonna have
Is the segmentation full?
Because we can only go to 11.
Oh, 'cause we have
Remember, ours goes to 11. So you see where the 2 1s popped up? We have 6, can take it to 11, and then 11, ooh, little sideness there. 11 can take it to 6. All right, let's add some more. What else you want?
2 and 5.
2 and 5. Directed or undirected?
Directed.
Ooh.
Try a little bit of both.
All right, what else you want?
3 and 7.
Directed or undirected?
Undirected.
7. I have 17, 38.
We don't have those numbers.
Any others?
3 and 4.
Directed or undirected?
Undirected.
Okay.
10 and 11. 10, 10.
That's already there.
How would you
1, 2,
0 and 5.
6. And then how about we do 11 to 9? All right, here we go. So the question is, can we go from 0 to 9?
Yes.
How?
Just call the undirected edge 0 to 9.
No. 0, 9. There's no edge there. But is there a path from 0 to 9?
No, possibly.
Yes.
Yes. How could we programmatically find that?
That's a good question. Go through the dirt.
Put a directed edge from at 0, 7, 0, 8, and I'm sorry, 1, 7, 1, 8, 1, 9. That allows a path to 0 to
1,
7.
6, you mean?
From 6 to 7 to 8 to 9, and then 0 to 9. You can create the path like that.
Or you can use
There is
the
no
ones
path
that are,
from 1 to.
I'd
or
say-
you can use the ones that
1
are
to
already
7.
made.
Oh no! Without creating more paths, without creating any more edges, is there a path from 0 to 9?
Can you go 0 to 1 and then
1 to
1 to 6?
6 to
6 to 11 and then it was 11 and 9.
yes. So how do we run a program to discover if there is a path? Google it.
there's an algorithm for this.
There. Almost correct.
Almost.
There are algorithms for this.
There's multiple.
How would you do this, Sydney?
Like programming.
She's got a point.
Jonah?
I would look above.
How would I do it?
Yes.
Ask it nicely.
Please, pretty please, sir.
Please, please.
I know where he's going.
See, okay, that should be our t-shirt. How do you do this? You ask it nicely.
Does path exist? And start and end. Probably should return a boolean.
That's what I should do this summer.
I thought you were going to say that's what I should do this summer, return booleans.
Yes.
All right. Okay, how do we ask it nicely? So am graph am does path exist? Is that what you want?
Yeah.
Okay. Y'all failed.
And make sure you be as nice as possible.
All right. Anything else? You want me to put pretty, please? Okay.
Polls. No, actually, no, here's what you put. You should put polls, but just put as many keys as possible. You see, have you ever heard that there's a correlation between the amount of keys and the amount of chance that it will happen?
Does path exist between 0 and 11? All right. Well, it says 0, but that's false. All right. So how can we do this?
But that's false.
What could we do? All right. Think back to your other data structures. How would we search other data structures? Rovers. All right. Recursively. How would that help us?
Iteratively? I don't know.
Iteratively.
I don't know if things out there. Throwing a dart start blindfolded.
We would have to think about how we would get there in the first place.
What are we doing? Are we looking?
What we're trying to do is we're trying to go from we're trying to go from here to here.
Right.
And so we need to think about how we would do that. And so in this case, what we can do is we just keep on going to the right a couple of times. We can see if we can do that. We can just keep on going that way, and if we can no longer go that way, then we can't go there.
Okay. So how would we code that?
So
Using a rope.
here's an edge.
Yay.
Go to that edge, but here's not an edge, and we need to go that way to
Well,
get
okay.
to
So
there.
we go to 1. All right. We're at 0, so we go to 1, and then we're at 1. What do we do?
And then we check if there's one this way, and there's not. We can also check if there's one this way, so we can go there. And we can keep on doing this until we hit a roadblock.
Okay.
And if we're there, then, then we're there.
All right. So what type of search is that?
I'm not quite sure the name of it.
Is it depth or breadth?
Did we learn this?
Yeah. Don't you remember binary trees?
I remember how
Depth.
painful they were.
They're not painful. They're the easiest. Such an easy data structure. So easy. All right.
An array that's 1 through 10 is an easy data structure.
Okay. So if you use depth for search, what are we using? Starts with an R.
Recursion?
There we go. Ends with an recursion. All right.
I said that earlier. I take credit.
You're going to take full credit for it?
I'll take half
Okay.
of it. So
Don't
generous.
sell yourself
So
short.
generous. Take 1/3 or 3/3, 2/3. Sorry. I'll just take the whole thing. More and more.
All right, so we want to set up the recursive call. So bool does path exist recursive and start end in, and we actually need something else. We'll find out what it is in a moment. So we'll just return does path exist recursive with start and end. All right, so what's the base case here? We have no idea. All right, good. That's fine. We will figure out the base case.
Oh, wouldn't the base case be you're there or you hit a roadblock?
All right, yeah. So if start equals end, return true, right? Because we're there.
Yeah, that would be.
So we really shouldn't call this start. We should really call it current position. Okay. Then what do we do?
Also, if current position's 0.
Well, what if we start at 0?
If current position's neighbors are 0.
So if we're starting at 0, where do we need to go? Yeah, so we need to go down the array. So we need to have another iterator. Vector of int iterator it equals what? Position dot begin. Oops. Dot end it plus plus. Okay. So this will go down the array.
Now we need to look for a 1. Right. So
If it equals 1, then what do we do?
Move on to the next one.
We write way down. Does path exist? We recurse. With the new point, which is, wait, what is the new point? Oh, we,
Good job.
next position equals 0. Next position plus plus. There we go. Next, next position and end. If found, return true. Otherwise, we're going to keep going. Right?
Yeah.
And then didn't find anything, return false, right? Okay. So what's the problem with this code? When I run it, do you think it'll compile?
It'll break.
Maybe.
Let's see if it compiles.
Let's see.
It did compile. What's going to happen when I run it?
It'll break.
What's going to happen that's so bad?
Is it gonna reset values?
I don't think it's resetting any values. Let's run it and see what happens.
Yeah, let's see.
Oh, seg fault.
Oh, that's
that's
a problem
fun.
right there.
Hmm.
So let's see, somewhere along the line here then, something happens. And we could probably debug it. Yes.
Let's do GDB on a.out. Let's run it. Can't access memory. Ooh, segmentation fault. This. That's not too helpful. I misspelled stack. Let's see. Type return. Whoa! You know what the problem is?
We're in an infinite loop.
We're in an
Yeah.
infinite loop. Why are we in an infinite loop?
Because maybe we don't have our base case for our can't find anything yet.
I don't think so.
So our problem is we're not marking where we have been.
Yeah.
Okay.
So we immediately go back to
Change
where
it
we
to a
just
2.
Hmm?
Change it to a 2.
change it to a 2. We could change it to a 2, or we could do something that is more correct. And we could create, I don't know, let's do a vector of int has visited, although it really should be booleans, right?
Yeah.
And what should be the capacity here?
You what?
mgraph am.size.
Yeah.
All right, and we really should pass that in.
Oh, that's what you meant.
What?
So that's what you meant by we need something else.
Yep.
Yeah.
So, if it's not the end, we should probably mark it as has visited sub current position equals true. So we're going to go through here. If it equals 1 and has visited sub it equals false, then we'll go in and recurse. All right, let's see what that does.
Oh, they didn't like it.
Yeah, that's because, again, we got to do that.
Yeah, you gotta specify that it's just the.
All right. Almost there. Note declared here. Oh, hold on. Let's try it again. That's right, because when we're down here, we recurse, we need to pass it again, has visited. And we really should be doing this by reference. So we're not creating one all the time. Ooh, still a seg fault.
Well, back to the corner then.
Ooh, sounds like the same one.
Wouldn't you also need to? Now I'm just spitballing here. Wouldn't you also need to change the has visited like after that boolean in that if statement?
And once we visited, we're good. Hold on. It's not IT. It's next. Oh, that was cool. Next position. I was using the wrong variable. So, fooled you. Oh, 1. It found it. Cool. Yeah, we won. How would we edit this to find out what the path it took was?
Wait, didn't it have return false though?
No, let's go print it out. Let's go current position, nice little arrow, end. I don't think it's going to actually print it out the way I wanted to. Yeah, I didn't think it would. We actually want it to look like this. Ooh, -1. Why is it? Oh, because the arrow is weird. There we go. So 6, 1.
So 1 is going to a 0, and 0 is going to be not visitable.
Hold on. There we go. 11, 6, 1, 0, and then there's still an extra 1 right there. Wonder why there's an extra 1. But where were we starting?
0.
Yeah, does path exist between 0 and 11? Print out an extra 1 for some reason.
Is that the one that, like, said we found it?
Maybe. But it's going 11, 6, 1, 0. Fortunately, I had to print it backwards. Oh, there's an extra 1 right there.
Maybe I just wanted an extra one.
I do like my extra 1s.
Yeah, I think that's just a return value. You found it.
That is the return value. You are correct. From up here. So let's put in a quick little. Yeah, much better. Yeah, we just have an extra error. We don't care about that. All right, so it found one. All right, and then even found the path. That's pretty cool. So what would happen though if we got rid of this? Would a path exist?
Got rid of what?
Oh no, let's test it.
Oh, 0 to 11. So let's test it. It should still exist. Should be the same path. The problem should be, well, if we want to go from 0 to 9, does that exist? All right, 9. There we go. But then if we get rid of this last edge, doesn't exist. Looks like that's working. So this is called a recursive depth first search, which you'll be doing for your lab.
Hooray.
Is this lab 22?
Yes.
Because we didn't assign that last class.
Yeah, it's lab 22. Well, that's because last class I assigned an ethics paper.
Cool. Yeah, we were.
But that never stopped you from setting a project in a lab at the same
What?
time.
I'm getting generous in my old age.
Did you say in your old age?
He just admitted that he's old.
How old is old, sir?
All right, so we're trying to go from 0 to 9, 1 to 6. We could also add some from 3 to 9, and then maybe we could add, what else could we add? We could add something from 6 to 3. Wonder which one I would find. No, I found the 3. We'll add it from 4. There we go. Did I get to do it? No, I found the other one first. Oh, from 4 to 9. That's what I want.
So does this just find a path, or does it find the shortest path?
That's what I'm trying to trick it into making sure it does not find the shortest path. because it would go from 0 to 1. Oh, 1 doesn't go to 3 yet. There we go. So 0, 1, 3, 4, 9. Let's go from 4 to 6. There we go. So now we're making it return a path, not the shortest path.
I don't really want the shortest path.
Did I ever say we wanted the shortest path?
I mean, we normally want the shortest
We normally want the shortest path. How would we write one that gives us the shortest path? And why is this not
Take out
giving us?
whatever you just did.
This is just a legal graph.
Yeah.
Perfectly fine. What else do we do? Let me stop the recording right here. Break it up.